Okay. Let me share my screen. I hope my screen is visible. Uh, so once again, I wanted to show where you can find the drive link and all the material. If you, I added the drive link over here. If you go to RL channel, right, under files, I added the drive link here. Click on that. I'm uploading all the material in my Google Drive, so you'll find it here. The main reason I'm using Google Drive is because it's easier to open the collab notebooks directly from here. Otherwise we will have to download it from if it's on the Microsoft, right, like we have to download it and again upload it to collab. So I'm using this, uh, and you will find the class notes over here under RL notes. I'll keep updating it after every session. This is the textbook, certain. This is the textbook, and under links, I'll be uploading all the lecture videos links. Okay, codes are obviously the codes that we discuss in every session, and then assignments are like the coding exercises or other like theory assignments that will be assigned to you, and all these will be graded, so make sure you submit this. Okay, if I open this one, you'll see the due date here. For this first assignment, the due date is 10th of February, which is next Saturday. Okay, it was like, I hope you all tried it yesterday in the lab. So 10th is the due date to submit this. Sudarshan sir will be sharing a link, a submission folder link. There you can upload all your collab notebooks. Okay, so because he will have all the submissions in one place for all the subjects, so he told he will only share the submission folder. uh, and these are the quiz questions. Okay, the first quiz questions are here, and second one also I uploaded. You will be working on these quiz questions today after the session. I hope that's it. And this handbook, this has some definitions and formulas. I'll keep updating it once in a while. So this handbook and the RL notes will be mainly your reference material for your sessionals and labs. Okay, and the codes. Yeah. Shall we start with the session? How many have joined? 21. Okay. Some of you have gotten back with the last week's quiz questions. Uh, I wish rest of you also try and get back with the answers. Even if it's wrong, it doesn't matter. Just you can give it a try, and uh, I'll tell you if something is wrong, right? Like, uh, try to give it a shot. Okay, let's have a quick recap of what we have done till now. So first we saw what different terms in reinforcement learning mean. They're agent, environment, state, and action. So agent is simply the robot or the driverless car that will learn to take different actions, right? It will learn to perform different tasks. That is the agent. Environment is the surroundings where the agent is present. It is simply the road or a house floor in the case of like a house cleaning robot. And state is the position or location of that robot or the car, right? Or it can even be the amount of charge that is present in the case of a driverless car or robot, and say how far it is from the charging point, or things like that. These things come from the environment. They are sensed from the environment. The state is sensed from the environment, right? And then action is the decision that the agent takes in order to move inside the environment, to move from one state to another. These actions are, for example, move left, apply brakes, accelerate, and things like that. Go back to the charging point. These are the decisions that the agent will make. So main goal of reinforcement learning will be to take actions such that the long term reward will be maximized. Okay, that is the main goal of reinforcement learning. Afterwards we saw what Markov decision process is. So, Markov decision process is sort of a mathematical framework for reinforcement learning problems. Once we frame the RL problem in using a Markov decision process, we'll be able to solve it. We will be able to make the agent take optimal actions. Okay, we'll see that in the coming sessions how we can train the agent to take optimal actions, but we this is a basic framework for reinforcement learning. To understand Markov decision process, we started with what a Markov process is. Markov process simply has a transition matrix, the state transition matrix, and it tells the probability of moving from one state to another, right? For example, if today was sunny, what was the probability of tomorrow also being sunny? From this matrix, it is zero point 0.8. Like that, we saw a simple example, and we have state transition diagram also. The same transition matrix can be represented in the form of a diagram like this, with arcs or arrows representing the transition probabilities between states. Okay, and then we came across the Markov property. Markov property simply means that the next state depends only on the current state, or in other words, state t plus 1 depends only on state t and not on any of the previous states. That is the Markov property. And what is the significance of Markov property? Markov property implies stationarity, due to which the transition matrix will remain same over the timestamps. This transition matrix which we have, right, it will be constant for every timestamp. After, like, say, 5 or 6 days, you don't refer to a different transition probabilities for the climate change. It will remain constant over the horizon, like for how many ever days we are predicting. If it is not stationary, right, the system will become kind of dynamic, and the Markov property is broken. So in those cases, they will have to look much behind. So this assumption must hold good in for this Markov decision process. We will make this assumption. It's obviously an assumption. In real world, this might not be the case, but using this assumption, we solve all the RL problems, and it's pretty good enough. Okay, and then we saw what Markov reward process is. In the Markov process, we did not have a reward matrix, but in Markov reward process, a reward matrix is also added along with the transition matrix. What does a reward matrix tell us? How much reward the agent will get for each transition, right? All the one step rewards are represented in the reward matrix. Say for from working on computer to going to have a chat with their friends, the employee will get a reward of -7. Or if he still stays on the computer in the next hour also, he gets a reward of +10. So this is the reward matrix. And the reward matrix and the transition probabilities both are represented in the state transition diagram as such. On all the arrows, the transition probability and also the reward was represented here, right? Do let me know if you have any doubts. We can discuss it again. And then we saw what return means. So return is simply the sum of all one step rewards, all the future one step rewards. Some of you have got confused on this, like GT is not the past sum of past returns. Okay, we are not worried about the past, we are worried about the future. To make a decision, we should make a decision based on, like, how much reward we get in the future, right? It's how much we got in the past is kind of fixed, there is nothing random there. So we need to make decisions based on how much or how we can maximize the future reward that we get, and hence return is represented as this formula. It is the sum of all the rewards that we get in the future, and these are all random variables, because the agent can take different actions, and different actions can take the agent to different states. Like, say it took an action to move right, but it may not always go in the right side direction. Only with a certain probability it might go to the right, and with certain probability it might stay there or go to a different position. So there is certain stochasticity here, so due to which all these are random variables. Then we saw what long term discounted return means. We just multiply a discount factor here, a scaled discount factor, and it keeps increasing non-linearly. The discount factor, the multiplication factor keeps increasing non-linearly, and thus since it is between 0 and 1, since it's a fraction, like between 0 and 1, the value will the multiplication weight will keep reducing along the successive rewards, right? So due to which what will happen, the return to calculate the return, we give more importance to the immediate rewards, and less importance to farther and farther rewards, right? That was the whole idea behind this discount factor. Why this is because, like, when we are taking a decision, we care more about what is going to happen in the next time step. Of course we have to care what happens after 10 time steps, but not as much as how much we care about the next time step, right? That is the idea. It kind of uh, weighted some, but in a decreasing order. And what is an episodic task? Like, the simulation will come to an end after certain time steps. Chess is an episodic task. And what else? This example, this computer coffee chat, this was also an episodic task. Like, we created episodes of 10 hours, right? Like, the employee is going to work for 10 hours, is going to be in the office for 10 hours, and after 10 hours the episode will get over. And this sunny rainy example, this was a non-episodic task because it never ends. It keeps going on and on, right? It's just how we formulate the problem. Any doubts till now?
No, sir.
Okay, we'll move to the next part then. Just a second. Okay. So we saw what Markov process is. Markov process had only transition probabilities, right? And from Markov process, we then came to Markov reward process. The reward matrix was added here, isn't it? Now we are going to see what Markov decision process is. So what will get added here? First we had transition probabilities, then the reward matrix got added. What will get added here to make a decision? Hmm? What do you think gets added here? Actions. Till here we did not have any actions in the examples that we saw. Here actions will also get included. That makes the Markov decision process. A Markov decision process has multiple states, and the transition probabilities between those states are also defined, and there is a certain reward that the transitions get. And along with all that, the agent will be able to take different actions also. Okay, so uh, previously we had only one transition matrix, right? I mean, there was one matrix representing all the transition probabilities, but now let's take an example where there are like three possible states, s1, s2, and s3, and three possible actions. Okay, a1, a2, and a3. So previously there was only one transition matrix, but now that is not the case. Depending on what action the agent takes, the transition probabilities will change. Okay, So let me draw that here. Say if the agent takes the action A1 at a certain time step, there will be one transition probability like this. We'll see this using a solid example shortly. S naught, S1, S2, S naught, S1, S2. Transition probabilities P0, 0. And say it took an action A is equal to A2, it will have a different transition probability. Does that make sense? Depending on what action it takes, just a second. Okay, depending on what action it takes, the transition probabilities will change. That is the whole idea. So a simple example here, say the agent tried to take an action to move right. Okay, so the transition probability, like say, uh, it was at, I will draw it like this: S naught, S1, S2, S3, and S4. S4 is not there, say it was only this much. And from state 0, it tried to take an action right. Okay, so S0 to S1, S2 will have a high transition probability, isn't it? But if it took an action to move down, S0 to S3 will have a higher probability. That's how I'm saying like the transition matrices are different here. We'll see this using a solid example. We'll using the epidemic modeling problem. And if it takes the action A3, it will be a different matrix. Okay. Now we'll see what value functions are. We have two types of value functions. One is the state value function, state value function, and the other one is the state action value function. The state value function, right? The first one, state value. The state value function simply means how valuable it is to start from a particular state. Okay. In the last week, when we were simulating the uh, coffee and computer, this example, right? So we simulated it over many episodes, I think around 1,000 episodes, and then took the average total reward, isn't it? And then we tried to tell like which state is it more beneficial to start from, isn't it? Which state was that? There was a slight difference in the total average return, right, in the last week's coding problem that we saw. Computer had a slightly higher average total return, isn't it? It was around 24, I believe, compared to coffee and compared to chat. Depending on the initial state it started, the total average return was different. So that is the same thing that we are seeing here. It is also known as state value function. It tells how valuable it is to start the state S. Okay, it is represented by this V pi of S. We'll see what pi is in a moment. What do you think this must be? What do you think this formula must be equal to? V pi of S. Any guesses? It should tell how valuable it is to start from the state S. It is very much based on what we had seen till now. Can you tell what it is? How would you tell how valuable a state is? Just try to give a guess.
How close it is to the final state we want to achieve.
Yeah, yeah. How close it is. To say how close it is, I mean, we should look at how much reward it gets, right? I mean, how high is
Yeah,
the reward? Yeah.
yeah.
So how will we write it in the form of a formula? Can you tell? You're going in the right direction. Yeah.
Summation of the
Maximum reward of that state.
Sorry, I did not hear.
Maximum reward that state can possibly offer.
Yes, yes, and it is given by what expression? That is correct. What is the reward that it can get from starting from that position, right? Isn't it represented by this long term discounted return? How much return it gets starting from that time step, isn't it? Since the states that it can go to are stochastic, we give it by this expression. Expected GT, but it should be condition on the state that it starts from, right? ST is equal to this one, small s. So given that we are starting from the state, yes, what is the expected long-term return that the agent might get? That is the meaning of this expression. Any doubts on this one?
so
Okay. This is like alphabets of Markov decision process. Everything will start from this state value function, and the other one is action value function. It is the expected. You understand what expected means, right? It is kind of average. Since it's a random variable, we don't call it mean or average, we call it expected. Oh, sorry. Why does it come up? Okay. Expected long term for starting from state S. In a similar way, can you tell what state action value function means? Is it slide of state action? What should this expression be? It is represented by q pi of s comma a. What should this be equal to? It is very similar to the previous expression. Can you guess?
Expected value of GD given ST is equal to S and SC is equal to A.
Fantastic. Expected value of GT, expected long-term return, long-term discounted return. We should always mention discounted because all these are discounted long-term returns. Sorry, first we'll write AT, sorry, ST. ST is equal to S and AT is equal to A. Okay. I don't know why this keeps sliding. Let me turn this. Hmm. Let me write the definitions now. How valuable it is to start from state S and take an action A. Okay, what and it is the expected long term return. Did I write? Oh, I forgot discounted long term. Discounted here also. For starting from S and taking an action A. Okay. Now, let's try to like expand this equation. First, we'll start from the state value function and try to expand it. Okay, what I mean by expand it is, let me write it here. So v pi of s is given by expected gt given st is equal to s, isn't it? So we have one property called expectation using conditioning. Expectation. It is similar to law of total probabilities. By expectation using conditioning, the expected value of random variable x is equal to another all the possible values of random variable y and expected value of x given y probability of y. So do you see this? Have you come across this equation before? Is it similar to law of total probabilities? Expected value of a random variable x is equal to the sum of the expected values of x given y weighted by the probabilities of y. Okay, so in a similar way, we can expand the v pi of s as summation of, see, we are starting from the state yes, and we can take any action, right? Say if there are three possible actions, we can take any of the three actions and go to different states. So we'll write summation of a belongs to capital A. Capital A is the action space, and then expected, what will be this one? Capital X is similar to gt, right? Given we already have st is equal to s here, st is equal to s, and we are since we are having a summation over all the actions, at is equal to a will get conditioned upon the action that it takes, and then probability of taking action at is equal to a. Let me write it a little bit to the left. Here there is a multiplication. This should match with this, isn't it? There is already a conditioning on state s in our equation, so that is there like that. It is not disturbed, and we are adding another condition which is on the actions, right? And there, so we got the summation over all possible actions, expected long-term reward given the agent takes the action A, and the probability of taking an action A. Everything conditioned on the state it is currently in. So this equation can is usually written in these notations. V pi of s is equal to summation of a belongs to a. So expected long-term return given that it is in state A and takes action A, isn't that same as the state action value function q pi of s comma a, isn't it? And this can be written as pi of A given S. We'll see in a moment what pi means. It is, consider it simply the probability. Okay, like this is a notation that they use for the probability of taking an action given that it is in a state yes. So this is one equation. Now we'll take the other equation, the state action value function, and expand it. What was the state action value function? Q pi of S comma A is equal to expected GT given ST is equal to S, AT is equal to A, isn't it? There is another property called expectation, linearity of expectations. We'll apply that property. Linearity of expectations states that expectation of alpha times, no, not alpha times beta, alpha times x plus beta times y is equal to alpha times expected value of x plus beta times expected value of y. So now from the above equation, we can write it as like this, isn't it? We'll expand GT now. What is the expression for GT? It is simply the sum of the future one-step rewards, right? RT plus 1 plus gamma of RT plus 2 plus so on, given ST is equal to S and AT is equal to A. I know it's a lot to sink in, but you'll get used to it as we go on. Like these are the only expressions that we'll be seeing through the entire semester. This is all that reinforcement learning is about. Okay, so we'll be looking at different methods to solve these equations. We'll be arriving at what is known as a Bellman equation in a moment. So once you have the Bellman equation, right, reinforcement learning is all about solving that Bellman equations, different ways to solve the Bellman equation. Okay, so by the above property, by linearity of expectations, see you had a scalar and alpha is a scalar value and x was a random value, right? Does this also look similar? R is a random rt plus 1 is a random variable, rt plus 2 is a random variable, and gamma is a fixed constant, it's a scalar value, constant value, right? So we'll apply, see if this is correct. Expected value of rt plus 1 given st is equal to s. See if I can write it in this way. I'm taking gamma outside here, rt plus 2. Is it correct? Any
Yes.
doubts in this? Okay, I have taken gamma outside here. There was actually one more, like if you write another term, it will be gamma cubed of rt plus 3, isn't it? So no, sorry, gamma square of t plus 3. So when we take gamma outside, it became gamma of t plus 3. Okay, so next what we'll do is, let's write this as it is. Rt plus 1 plus st is equal to s, at is equal to, this is the only derivation that we are going to see in this semester in reinforcement learning. I need to do something about this. It keeps sliding away. Okay, so gamma of expected, what is this now? How can Does it ring any bells? This expression rt plus 2 plus gamma of rt plus 3 and so on. There will be a gamma cube of rt plus 4 and so on. What can I write this as? Hmm? Is it not gt plus 1? Gt plus 1 given st is equal to s, comma at is equal to a. Next, what we'll do is, again by the same property, the previous property, expectation using conditioning, given that the agent uh, starts from state S and takes an action A, he can go to any of the possible states, right? He can go to one of the possible states. So we'll apply that expectation using conditioning and add a summation over here. Starting from state S, taking an action A, he will go to the state S prime, okay, belonging to S. Probability of S prime given S comma A. What does this mean? What is the probability of going to the state S prime given that you are starting from S and taking an action A? Then R of S A S prime. Now we know that the agent has moved to this state S prime, right? Hence, this is not a random variable. It's from the reward matrix. What is the reward for starting from state S, taking an action and moving to the state S prime? And then plus gamma of, we'll add the same conditioning over here. The condition by conditional probability, the agent can move to any of the states at time step t s t plus 1, right? So s prime is equal to s probability of s prime given s comma a. And then this term I'll write it down, gt plus 1, rewrite it, gt plus 1 given. Now see, at time step t, it was in state S and took an action A. Now at time step t plus 1, we are conditioning it on, right? S t plus 1 is equal to S prime. Let's write down the other two conditions as it is. Okay, a comma here. So there are three conditions over here. Now by Markov property, what we know that the next state depends only on the current state and not on any of the previous states, right? So gt plus 1 kind of starts from rt plus 2, right? So rt plus 2 should only depend on the state that the agent is in on the current time step. Current time step is t plus 1 now. It's not no longer t because a transition has happened. The current time step is t plus 1, and next time step rt plus 2 depends only on the current time step by Markov property, right? And thus we can like simply scratch off this. Let me scratch it using a different color, right? Now what we can do is we can take this summation of p of s prime given s comma a common. It's common between both the terms. Let's take it common. S prime given sp of s prime s comma a. What do we have inside the big bracket? One step reward for taking an action A starting from state S and going to the state S prime, plus this has become taken out common. Forgot an expectation here. Expected gt plus 1 given st plus 1 is equal to s prime. What can you tell about this expression? Can you tell this in plain English? What this means? Can anyone tell?
Expected long-term discount
Hmm, hmm. Given that,
given given the current status as prime.
yeah, yeah, that is nothing but that is the definition for. i- Isn't that the definition for state value function? Let's revisit state value function. What you said is this, isn't it? It is the expected long term discounted return for starting from state. Yes, instead of s, there the starting state was s prime, a different state, but still it's the definition for state value function, isn't it? Instead of s, we have s prime there. Awesome. So can I write it that way? Yes, yeah, I wrote the one step reward. Can I replace it with the same notation? Okay. How valuable it is to start from the state S prime. That's what it means, right? That's it. Our derivation is over now. This is q pi of S comma A. Let's look at different parts of this equation. Given that we are in the state S and take an action A, we can move to any of the possible states, right? If there are three possible states, we could go to any of the possible states. So after moving to that state, we get a one step reward. This is a one step reward. How do we move to different states? It's based on the transition probabilities. These we had the transition matrix, right? It can also be written in this format here. Transition, what is the transition probability of moving from state S to S prime by taking an action A? So we are just applying conditional probability here. With different probabilities, we can go to different states. And what will happen when we move to a particular state? We get a one step reward plus the discount factor that we have. Since we the transition has already happened, for the next time step, there is a discount factor here. And then we multiply it with how valuable it is to start from the new state S prime. Okay. Do you want me to repeat this? Is it clear or uh, it's fully a bouncer? We'll look at these equations using an example now, not an example, using a backup diagram, what is known as a backup diagram. Backup. If you haven't understood anything from what I said till now, I mean the derivation, if you have not understood it, it's okay. Now look at this backup diagram and try to understand it. It's not related to what the derivation was about. Say there are two possible states and three possible actions. I'll write the state space like this: S1, S2, and action space like this. Okay, A1, A2, and A3. Let's draw a backup diagram for this. Starting from state S1, the agent can take one of the three possible actions, isn't it? A1, A2, and A3. And when it takes each of these actions, it can again go to one of the possible two states, S1 and S2. Say it started from state S1, took an action A1 with different transition probabilities. It can go to state S1 and S2, right? Everything is stochastic here. Only the agent can decide what action it is going to take. So uh, the probability that the agent takes an action A1, given that it is in S1, it is given by this, right? P of A1 given S1. It is the probability, and taking an action A2 is this. Taking an action A3, probability of taking an action A3 given that it is in S1. This pi simply means the policy. It's the probability itself. It represents with how much probability the agent will take what action given that it is in a particular state. Okay, so if you add all of this, it should result, it should be equal to 1. Okay, if it's deterministic, one of these will be equal to 1 and the other two will be 0. But if the actions are stochastic, then the sum of all of them should be equal to 1, and they can have different probabilities. Yeah, you got the point. So now the transition from A1 to S1, right? I mean, from S1 to S1 by taking an action A1, that is represented by the transition probability. Starting from state S1, taking an action A1 and S1. On this side, what will it be? Transition probability of starting from S1, taking an action A1 and moving to S2. Does this make sense? I have simply written it in the form of a diagram, all the notations that we saw till now. Just to, what is the other notation for this? It is simply probability of taking an action S2 given that you're in the state S1 and take an action A1. It can be written in this way also. So now let's see how that conditioning happens. If I say how valuable it is to start from the state S1, we should add the all of the values of each action the agent will take, right? Like, so let me write it, see if it makes sense. The first one, and q pi of S1 A1 plus pi of q pi of what is the third probability? A3 given S1 q pi of S1 A3. Is that correct? How valuable the state S1 is equal to the summation of all the state action value functions weighted by their corresponding probabilities. If say it was deterministic, and the agent will always take an action A1 when it is at state S1, so these two will go away, right? These two will go away, and we will have only the first term. So depending on the probabilities, each action value function gets weighted here. Now I'll write this as a summation. Summation of A belongs to capital A, pi of A given S1, q pi of S1 comma A. Is this clear? Any doubts in this?
No.
Okay. You see that this is same as what we derived earlier, isn't it? Here, this was same as this, but we just fixed the starting state. That is the only difference. So in a similar way, you can also write it for action value function. See, when you start it from the let me choose a different color. When you this is q of s1 a1, right? Say you're starting from s1 and taking an action a, and you ask how valuable it is. It will come down to this equation here. So it can go to one of the possible two states. With what probabilities? The trans from the transition matrix we have the probabilities. And whenever a state transition happens, right, there is a one step reward that comes out, plus the one step reward plus the discount factor of the value of next state. We will try to write that as well. Starting from state a1. So state S1, we move to A1. So this is the backup diagram that we had. Do I have to rewrite it? Mm, 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 mm. No, we don't have to rewrite it actually, but yeah, anyways, let me just write the probabilities. Probability of taking an action given that it is in a state S1, and this is the transition probabilities. I write it in this format now. Probability of going to S1 given that we are in S1 and take action A1. Probability of going to S2 given that we are in S1 and take action A1. So now what is Q pi of S1 comma A1? This is the question, right? So from by taking an action given that from state S1 we can go to one of the two possible states. So let's just write it one by one. P of S1 given S1 comma A1, and the other summation is P, other term is P of S2 given S1 comma A1. So what will be there inside this? We cannot directly write how valuable it is to start from state S1, right? Why can't we write it directly like that? Because there is a one step transition that has happened, so we cannot directly jump there. There is already a reward that the agent gets for the transition that has happened. So it is given by this one step reward for moving from S1, taking an action and stay moving to S1 again, plus and the discount factor. When the transition happens, we need to discount the further returns the agent gets. Again here, S1 A1 S2. We'll have an exercise. Once you write it, you will get the practice. It will be new now. I'll write it as a expression using summation of s prime given s p of s prime given s1 takes an action a1. I should do something about this, it keeps sliding away. Reward for starting from state s1, taking an action a1 and moving to s prime, plus gamma of v pi of s prime. This is q pi of s1 a1. We had derived it in a very formal way earlier, and this
हेलो
is
वन
also a
सेकेंड
same thing. Yes, yes.
एक सेकेंड एक सेकेंड हाँ जी बताइयो क्या कर रहे हो
Is it Achal? Can you go on mute, Achal, please? Oh, it's Aditya.
सॉरी सॉरी
It's okay, it's okay. I thought the voice was Achal's voice. Okay. Okay, is it clear, guys? We saw how to arrive at these expressions in two different ways. One was a very formal approach and other was using a backup diagram. Let me highlight this. All of you have slept, too much theory.
Nice one.
Okay. So this derivation won't be in syllabus. Derivation meaning the formal one that we derived using linearity of expectations and expectation using conditioning, only that won't be there, but using the backup diagram is important. Okay, this will come up. You need to understand how you will draw backup diagrams for state value and action value functions, and you should be able to write down the equations. It is just a simple conditional probability. Okay, like if you're able to go to starting from an action, if you're able to go to two possible states, then you write this kind of probability, like a probability of moving to that state. But if you are in a particular state and trying to take different actions, which is the state value function, you can take one of the two possible actions, so you will condition it on the actions that you take. So just keep in mind whether you should condition it on the actions that you take or the states that you go to. Okay, two equations are two types of conditionings. Now now what we'll do is we will represent uh, uh, see what we have here is, consider the state value function. We have action value function also in this, right? That expression is there. We will get rid of this by substituting q of s comma a from this equation. Okay, we'll write it that way. That will then we'll arrive at what is known as a Bellman equation. That is why we are doing it. V pi of s is equal to, when we are starting from state, yes, I get confused sometimes. So this is how I arrive at the equation. I'm starting from state s, so I can move to different actions, and thus I need to condition it on the actions. Okay, and when we condition it on the actions, we have those probabilities given that this one and q pi of s comma a. Now let's kind of substitute the expression for q pi of s comma a here, so that we don't have another function. Everything is in terms of state value function v pi of something. You'll see that in a moment. V pi of a comma s, and then here there is another summation. What should this be conditioned on? Like you're in a state s and took an action a, so you can move to one of the possible states, right? So we should condition it on the states. Probability of s prime given s comma a, and then we'll get a one step reward. Whenever we go to another state, we get a one step reward. And then since we have one step reward, we also have discount factor of v pi of s prime. There you go. This is known as the Bellman equation for state value function. Can you tell what are the knowns and what are the unknowns in this equation? Is this transition probability already known to us? Is it, what I mean by known is it there in the environment? Is it from the environment, or the agent has to decide? Okay, so is the transition probability given by the environment itself, or the agent decides the transition probability? If the agent decides it, the game is over. Like, we have complete control over the environment, right? So this
It's
transition
given.
probability, yeah, it's given by the environment. Good. So probability is also given to us, and reward is also from the environment itself. We don't have, the agent doesn't have control on the rewards that it gets. They are fixed. We can only take different actions to maximize the reward that it gets, but the reward matrix is fixed by the environment. And we decide this pi of a given s, right? Let me, we in the sense agent decides. So the agent decides this expression pi of a given s such that each state must have maximum value. So other two are just v pi, right? Agent decides what the transition probabilities, I mean probabilities of taking actions are, such that the values are maximum. That is the goal of the reinforcement learning problem. Come up with policy, with the act come up with probabilities for actions such that the value function is maximized. Okay. Other two, the transition probability p and also the rewards are already given by the environment. So agent have to decide the policy pi in order to maximize we are just like functions, right? I mean they are the value functions. Whichever state you plug in, it will give a different value. Okay, let's write down the Bellman equation for action value function. Given that you're in a state S and take an action A, you can move to one of the possible states P of S prime given S comma A. One step reward and the discount factor multiplied by, now I won't write down the same v pi of S prime. Instead, sorry about that, v pi of S prime. Instead, what I'll do is I'll expand it. Okay. V pi of S prime can be written as summation A belongs to A prime. Now pi of A prime given S prime. Now we have gotten rid of the state value function. Instead, we have only state action value functions. This is known as Bellman equation for state action. Any doubts here?
No.
We'll have a break at 12:40. Okay. We'll just see one more thing and then have a break. For any MDP, before we go there, let me write down what policy means. Policy pi, right? What is policy? If I write pi of A given as we have been seeing it till now, can you tell what policy is? Hmm? Policy is simply the probability of taking an action A. At is equal to A, given that it is in state yes. Okay. So this is decided by the agent, not the environment. Now, for any MDP, there exists a policy pi star such that V pi star of S is greater than or equal to V pi of S. So what does this mean? For any Markov decision process, there exists a policy such that the value function under that policy will be maximum, right? Say Kirtana will give me a policy, Aditya will give me a policy, and Achal will give me a policy. If I calculate the value functions of all three policies, one of them will be higher, right? But there also exists another policy known as the optimal policy, which will always maximize it, maximize the value function. That is known as the optimal policy. We train our reinforcement agents to come up with this optimal policy. How close it is to the optimal policy, it cannot ever get better. So policy simply determines what actions the agent takes, right? So an optimal policy will determine what are the best actions in order to maximize the value functions. Value functions is simply the long term expected return that the agent gets, right? Long term discounted return that the agent gets. So the RL agents should come up with this optimal policy such that it will maximize the expected long term return, right? Similarly, under the optimal policy, even the action value function will be maximum compared to any other policy. Okay. Under the optimal policy, the state value function and optimal value functions will have maximum output. So for any given state, if it's an optimal policy, that value will be the maximum. You come up with any other action policy, that you cannot make it more than what it is for an optimal policy. That is the whole idea. Do you want me to re-explain this, or is it clear? So the goal of an MDP would be to come up with a policy that would maximize these functions V pi of S and okay, I hope you're all back. So have you tried the programming exercise, the labs programming exercise? It was to explore a gym environment, right? Have you started working on that in groups? Have any of you not started it?
I actually worked on it alone and I submitted one.
Who is this? Sorry,
Kirtana.
Kirtana. Yeah, Kirtana. You worked on it alone, is it? I haven't gone through your submission yet. I'll go through that. That's
Okay.
okay. You can work on it alone also. Even Achal had submitted it. I'm yet to go through that. But yeah, uh, others also please start working on it. Like select a gym environment uh, and also Mithilesh submitted it yesterday night. Mithilesh, did you work on it in group or individual?
Yeah, individualist.
Okay, okay. So let me open that. And also, you will have to submit it in the folder that Sudarshan sir will share individually, okay? Because he'll be taking care of the grading. Don't forget to post it there. Just have the codes ready, and once he shares the folder, just submit it there. So this is the okay. Just a second. I'll connect it to the keyboard. Please give me a minute. This is the code that I had shared with you all. And the task was to select a gym environment and understand it, right? It's not connected. Just a second, my mouse is not connecting. Yeah, it's here. So let me quickly tell you what the task is about again. If you Google OpenAI gym environment, OpenAI gym, not the beta one, let's go to the usual gym environment, stay in gym. So they have developed multiple environments like this. They don't give us the agents. If you want to have the agents, you can go to other libraries such as TensorFlow, and there are a few other libraries. They will give you the agent is basically the one that makes the decision, right? It is the reinforcement learning model, in other words. But we need an environment to with all the dynamics physics in it, right? So that we can move our agent and try to make our agent learn. So they have given they have developed or programmed a few agents like this. Some of them even have the physics in it, like the gravitational force and things like that. Everything is programmed in that, and there are many. So you can choose an environment of your choice. Atari will be slightly complex. These are the games, so there will be many states and actions in that. Maybe what you can do is you could choose classic control, or what else are there? Even in box 2 there are a few. So you choose an environment which is like not too complex, and try to understand what the action space and the observation space in it is. So I chose two environments. One is the mountain car, and the other is frozen lake. So if you do that environment dot observation space, you will get the all possible states that the agent can be in. So in this case, the yeah, is someone saying something? Any doubt? Okay, so in this case, in the case of a mountain car, the observation space was like this, the action space was like this. Okay, like it could be at any location on the x-axis, starting from minus 1.2 to plus 0.6. Maybe it's in meters, or I don't know, but they mean something. Okay, like, and they calculate it based on the gravitational force and all that physics is like coded up inside the environment by OpenAI for us. So it can be in one of the possible states, the locations, and it can be moving with a certain velocity, starting from minus 0.7 to plus 0.7, negative indicating it's moving in a backward direction. So this is how I want you to kind of understand what the environment is about. And in this case, actions, there are three possible actions: either to go straight, go backward, or to stay where it is, no acceleration, right? whether to accelerate front, whether to accelerate back, or stay where it is. Three possible, that is represented like this discrete three, like that. Okay. So and by taking random actions, it did not go anywhere. And by taking an action that is slightly intuitive, uh, what I'm doing here is, if it is probably accelerating back, probably moving backward, I'm accelerating to further go backward, something like that. Okay, so I did that with this policy. It's a hard coded policy. It is not a learned policy. Through if and else conditions, we are hard coding it, right? So with this type of policy, it was able to achieve a slightly higher reward. I mean, it was able to go to the goal. So what I did here is, if the velocity was negative, I accelerate in backward direction. So it comes back more down and reaches. The other one was frozen lake. See, the state space here is 16, meaning 16 states are possible. 4 cross 4. It's a 4 cross 4 grid world, right? And then there is this action space which is discrete 4, which means 4 possible actions are present. How I'm able to say all this is because I went through the GitHub code of this. If I just do GitHub frozen lake, I'm audible, right?
Yes.
Hello. Okay.
Yeah, yeah.
So what I want you to do is go to the GitHub page. So get used to seeing all the codes like this on GitHub, because even in work we will be having to do like this all the time. And also they expect us in work to write doc strings like this. We need to explain everything what the code is about, okay, so that someone else reading the code will understand it. uh, it's kind of compulsory in the professional course that we write. So yeah, anyways, how I understood the action spaces, I came here and looked at what each action represents. 0 represents left, 1 down, 2 right, like that. And observation space is like this. It's 4 cross 4 observation space. The 16 states are represented from 0 to 15. They're calculating it in this way. It's probably the row that it is in into number of rows. So start, if it's in zeroth row, it will just be like 4. 0 into 4 is 0, plus the column that is in it. It will just be 3 in that case, right? It simply means like 0 to 15 are the possible states, and the actions are 4 possible actions. Like this, I want you to understand it. And if your the environment that you have chosen is simple enough to hard code actions in that way, to come up with a policy in this way, like hard code some conditions, if and else conditions. If it was this environment that you had chosen, right, then how I would hard code it possibly is, if it's in the first row, I would take an action, right, except for the this state 0 1 2 3, except for the third state. No, not even like that. uh yeah, I can do this, right? If it's in the third column, which means it's in the state either 2 uh, uh 2 6, I think this is 6. So like that, hard code something. If it's in the third column, I'll take an action to move down. And if it's in this block, if it's in the 14th block, I'll take an action, right? So for only for a few states, if you hard code it, you will get a much higher reward. In this case, it never reaches the present. For the one that I ran, it came and fell in this hole, right? I can't rerun it now because I need to connect it and do a lot of things. But yeah, that is the whole idea. You can hard code it in that way, something like you can even set conditions for each of the possible states. If it is in state 0, take an action, right? If it's in state 1, take an action, right, like that. Since it's a toy example, okay, so explore it that way. And also in this case, if you can modify this to 16 cross 16, so it will be a big grid. How do they do this? They have these hard coded, right? Not 16 cross 16, 8 cross 8. So if the parameter is 8 cross 8, it creates a grid like this. And if you don't pass anything, it will just be random. Okay, so I want you to understand such things from the environment that you choose, and make a document, not a document, you can write it in the markdown here in the code itself. Okay, it's clear, right? So the due date for that is on 10th, I think. In this 12th week, in the week of uh, in the third week, your sessionals are starting, right? First sessionals are going to start.
Oh, yes.
So yeah, so try to finish it either today or tomorrow, I suggest that. And the assignment next week is going to be helpful for your sessionals only. I'll make sure of that. Okay, let me go to the epidemic modeling code. And many of you haven't submitted the quiz answers of last week. Is there any problem in understanding? Do let me know if you're not understanding something. We can go through the concepts again, maybe in the evenings, or sometime like Sundays or Saturday evenings also. We can connect either individually or group and review the concepts. Okay. Or if you are careless, then don't be careless. That's it. Like, don't be ignorant of what is going on in the class, or yeah, we won't get anywhere by being careless, right? The quiz problems will just take like 15 minutes or max to max half an hour. If you haven't listened to the class, then maybe if you're googling stuff and submitting, it might take half an hour. Some of you have submitted from chat gpt the answers, but yeah, still the number of people submitted are like really less. I think around 10 or 11 have submitted. Hmm. Let's go through the epidemic modeling code. So today we saw Markov decision process, right? Open up this code, okay? All of you, just open up and let me know once you have opened it. I'll start going through this. You know where to find, right? Go to the drive link and then click on codes. You will find the last week's code. Did you find it?
Yeah, we found it.
Okay, okay. Please open it and connect and run it till here. Till the coffee example, you please run that. And also make a copy of it because you can't make modifications, right? If you have opened the same code. In the last week, if you have filled up all these other cells, then you can use the same notebook. Otherwise, make a copy of it and run it till there. Is anyone still opening it? Let's wait for a minute. Okay, I hope all of you have opened it. So now, today in Markov decision process, we included actions also in the setup, right? First, in Markov process, we had only the transition probabilities, and in Markov reward process, we had the reward matrix as well. And with reward matrix, we saw this example where there were transitions from one state to another, and there were different rewards assigned to each transition. Then we tried to take an average of the total reward that the transitions get for different starting states, right? And it was something like this: when the average return when the start state is computer was 25.9, it was approximately this, it was getting converged. I ran it a few times, and for coffee it was the lowest, and from chat it was slightly higher. It is kind of surprising, right? Always when things move to chat, we had given a high negative reward, but still it says it's good to start from chat, maybe because when it started from chat, it will either go to coffee or computer and get a higher reward, right? So yeah, uh, this is also what is a long term expected return, isn't it? GT, E of GT that we saw today in the uh, theory. Okay, next we are to, in order to include actions, there isn't this example is not good enough to add actions in it, so we'll look at epidemic modeling example. In order to add actions, there will be rewards in it, actions in it, transition matrix in it, making it a Markov decision process. Okay, so now there are four possible states that a person can be in: susceptible, infected, recovered, and deceased. About that, susceptible, infected, recovered, and deceased. Susceptible means the person can acquire the disease, he is susceptible to get a disease. Infected means he is already affected by the disease. Recovered means he has acquired immunity, they won't get the disease again. He or she will not think of the COVID scenario, so she won't get COVID again. And deceased means they have died, okay, because of the disease, not for other reasons, because of the disease they have died. We don't cover other reasons in this for the death. Above states can be encoded, we'll be encoding them as 0, 1, 2, 3, the states. And the transition probabilities are like this: given that the individual is susceptible, with a probability of 0.8 they will still be susceptible, and with the probability of 0.2 they might get infected. The time frame here could probably be like, uh, say a day itself. Today they are susceptible, tomorrow there is a 80% chance that still they will be susceptible, and 20% chance that they get infected tomorrow. We have not included actions here, keep that in mind. So there is only one transition matrix. Once we include actions, there will be multiple transition matrices. Depending on what action they take, these probabilities will change. Okay, so say today the individual is infected, there is a 70% chance that the individual will still be affected tomorrow, 20% chance of recovery, and 0.1 chance of uh, uh, being dead. Okay, so, and once they're recovered they will remain in recovered, because they will, we assumed here that they will get immunity. And once they're deceased, they will be in the deceased state, they won't come back to life. That is the assumption here. Okay, so the transition probability matrix is represented by a 4 cross 4 array in T. Let me rerun that. And there is one more thing here: initial state probabilities. Can you tell me what this means? Zero point 0.9, 0.101. Can any of you tell like what it could mean, initial state probabilities?
There's a chance of existing in those,
The
probably.
transition probability.
I got two answers. Not the transition probabilities, it is the chance of existing in those states. In the initially, it is the probability of existing in each of those states, right?
Yeah.
Did the other person say transition probability or initial probability?
Yeah, I said chance of existence, I think.
Okay, okay, okay. Right. Okay, anyways, so yeah, let's assume that there were 20,000 individuals. Based on the initial probabilities, if we multiply this vector, this array with 20,000, right? We got these numbers. So initially, based on these probabilities, among the 20,000, 18,000 were susceptible, 2,000 were already infected, none of them had recovered, and none of them were dead. Okay, does this make sense? So for COVID and all, like the World Health Organization used to suggest some of the norms, right, or the policies or rules to the governments, depending on these transition probabilities like this. So if they tell the Indian government to or if they suggest Indian government to set up lockdown for the next 6 months, they would obviously ask, why would I do that? What is the benefit that I get, or what is the loss by not doing it, right? The World Health Organization should give numbers in those cases, like if you don't do this, 10,000 people are going to die in the next 6 months, like that. So even statisticians like that do epidemic modeling like this, much more complex. We are seeing a toy example of epidemic modeling, and then come up with those numbers. Okay, we'll see how to come up with those numbers in a moment. So yeah, we'll start with the initial population state, which is like this, and then based on the transition probabilities, we'll make the system evolve. Okay, so initially these are the numbers, and people will take different actions with the sorry, not actions, they will transition to different states based on these probabilities, and in the next day this vector will change, right? There will be different number of infected people, different number of susceptible people. I hope you got the point. We'll do that for 100 days. Okay, so when I run it for 100 days, and let me also print the evolution here. Okay, see here. So now we initialized this evolution matrix to initial state probabilities, which was this. Okay, 1,800 people, 2,000 people, 0, 0 in all the four states. And then what we did is we took a dot product of the current state, this state dot product of this, with the corresponding transition probabilities. So if we multiply the probability here with this matrix, it will give us what is the state of next day, right? What is the state of population on the next day? So number of susceptible people slightly decreased. It was around it became 1,400, and 5,000 people had gotten infected. 4,000 people have got, no, sorry, 400 people have recovered. 200 have deceased, I guess. Yeah, from 2,200 got deceased. So like that, we run the loop over 100 days to get this evolution matrix. Okay, so it will have 100 rows, and each row representing what is the state of the population. Is this okay? Or do you have a doubt in how this dot product works? See, the current state, this is the number of people in the current state. We multiply it with the transition probability matrix. Let me do that here. Initial, let me multiply initial population state with the transition probability. See, it gives me the state of second day, right? First day, if this was the numbers, in the second day, this will be the number. How am I getting that? We are multiplying a 1 cross 4 1 cross 4 matrix with a 4 cross 4 matrix. So we still get a 1 cross 4 matrix, but everything will get multiplied with the corresponding transition probabilities. Okay, So we run this 100 times by updating the current state, and then the system evolves like this. So see, initially the number of susceptible people were around, how many were there? 18,000. Initially the susceptible, let me open this in a new tab. Initially the number of susceptible people were 18,000. 2,000 of them, yeah, 2,000 were infected. And then what happened? Infected people kept increasing and susceptible people came down, and also the slowly people started dying, and around it stagnated around, I think, 5,500 or something. Does this make sense? The recovered people also were increasing. Now we'll see, by taking different actions, how will this evolution change. We want to decrease the number of deceased people, right? So people have to be more aware of the situation, they should not go out and stuff like that. So that transition probabilities will also change, so less people will start dying or getting infected. If we change the transition probability matrix in such a way and assign that to the uh, for the evolution, we will see that the number of deceased people will come down. Okay, here after a certain state, maybe after 20 days, the number of dead people did not increase. Why? Because almost all of them had acquired the immunity. So now let's add actions to this. uh, Three actions are possible. One is to be careful, meaning following the rules that the government will set, the uh, 2 meter distance and things like that, right? Wear mask always, uh, and do not go to crowded places like that. If an individual is following that, or if an individual is ignorant, or if, meaning the individual is adventurous, they go out and for partying and stuff. When there was COVID, people did that, right? And things went bad. So that is another action that the individual might take. And the other one is extremely careful. So extremely careful people are like, they won't even go out at all, they order stuff online and things like that, who are like too careful. So let's also build these transition probabilities. Now since actions are involved, as I told, we'll have multiple transition matrices. Okay, let's fill up those. Can you tell what numbers I can put here for, if they're ignorant? Let give me a second. So if they're ignorant, right, the first row will always represent being in susceptible state, and the columns are like susceptible, infected, recovered, and deceased. So if they are more ignorant, there is a higher chance of getting infected, right? So I will modify the transitions like this. Point 0.7 is the probability of still being susceptible, and 0.3 is the probability of becoming infected. Okay, see here, the order is like this: susceptible, infected, recovered, and deceased. If they are ignorant, meaning if they are adventurous, 0.7 will be the probability of staying susceptible, and 0.3 will be the probability of getting infected. I'm cooking up these examples. See if they make sense. You can write the numbers differently also. Okay, so if they are already infected and they are given that they are ignorant, what is the transition probability that I can assign here to still be uh, infected? Let's say reduce this a little bit and increase the probability of becoming dead. Let the recovery, or I'll just do this. The probability of being infected is same on the next day also, and the probability of recovery might come down if they're adventurous, 0.15, and probability of death increased. Okay, keep in mind that all these probabilities need to add up to 1, 0.15. To the add up to 1, 0.15 plus 0.515 is 0.3 and 0.7 plus 1. From recovered state and from deceased state, there is no change, as they will remain in that state once they reach that state. Let me add it for being extremely careful also. If they're extremely careful, there would be a higher chance of being susceptible. When they're susceptible, you even more than how much it was for being careful, right? 5. And now, given that they are infected, how would it be? There would be a higher chance of recovery, isn't it? Let me reduce this to 6. There is a higher chance of recovery, and 6, 7, 8. Let me make this 3.5. See if it adds up to 1. Yeah, it does. Okay, we have created some transition matrices, considering how the person might transition to different state by taking different actions. Now let's run it for being extremely careful. Okay, uh, yeah, let me open this in a new tab. See, now number of dead people have come down, isn't it? It's around 2,500. Before it was so high. If the person is extremely careful, it has come down. Let's try it for being the ignorant state. If the person is being ignorant, and the thing to note here is, at every time step, here we are simulating it for 100 days, right? We are assuming that the action taken is ignorant for all the 100 days. Okay, things might not be like this. People might be ignorant initially and then start being extremely careful also, but here we are simulating it in that way. So this is how the statisticians will like give the numbers. Like, if they pass a rule to be extremely careful, meaning a lockdown is being passed, then how will the result of the population is going to be? They calculate it in this way. So we fixed the actions to one thing always for the 100 days. Let's see for being ignorant quickly. See, as it has the number of deceased increased. See, it was very less. It has increased around 10,000. For being careful, it is 5,500. For being extremely careful, it's 2,500, and this is different. For some reason, recovered haven't shown up, right? The number of people who have recovered, probably nobody recovered in this. I don't know. Yeah, the transition to recovery was so less that maybe nobody recovered, I believe. No, it was the ignorant one, right? Yeah. Let's see how many people had recovered in this. So I'm trying to get the last row of this matrix. See, like literally no one recovered from the disease and got an immunity. It is so less. Oh no, wait a minute. Recovered is 1,000 here, I believe. But it has not printed for some reason. I don't know why. I'll check this anyway. Probably because 10,000. Okay, let's add actions to this. Okay, I mean, sorry, let's add rewards to this. For every transition, right, from the starting state to the next state, given that we take a particular action, the person should say get a reward. Okay, let the rewards be in this way. If the next state is 1, meaning the next state is infected, the reward is -2, because when once they're infected, they cannot go to the uh, office or to college, right? So there is a slightly negative reward on that. And there is also a chance of being deceased, so we are giving a negative reward. And if they acquire immunity, meaning if they recover from the disease, we'll give a reward of +10. And if the next state is 3, which means they're deceased, we'll give a reward of -20. Okay. If we add rewards for every transition, and here if we run it for one particular individual, okay, this is how it happens. Here I'm not trying to make the population evolve. Instead, we'll consider one particular individual and set the starting state to 0. See, current state is what is 0? It is susceptible, right? So the individual starts from being susceptible, and the action that he always takes is being ignorant. So the states that he will see are like this. From susceptible, he this is random, it keeps changing for different runs. So for one particular episode, it was like this. From being susceptible, they got infected. Until the 5th day, they stayed infected and then recovered. Okay, let me rerun this. See, they remained susceptible till the 3rd day and then recovered. Yeah, in this one, you see, from susceptible, they went to infected and then deceased. The reward is -22. You could also try taking different types of actions. This is for ignorant. What was the other one? Let's try for being extremely careful. Now we are getting a positive reward, isn't it? It was mostly 0 or negative previously. So we are getting a positive reward now. So they kept being susceptible and infected and recovery has a high positive reward. So the total return is +6. So similar to the last lab, what I want you to do is, I want you to start from different states. Okay, from being careful, from being extremely careful, and from being ignorant. No, sorry, take different actions and then tell me what the total average return is. Let me say that once again. Fix the current state to 0. Okay, they will start, say they will start from susceptible. I'll write it down here. Susceptible. And calculate the total average return for taking different actions. So what you need to do is, now for being extremely careful in one episode, this is the return, right? I want you to run it over, say, like 1,000 episodes and take the average return. That will be for the action extremely careful. For let me do a few episodes here for being extremely careful. See, now it's -14. First it was 6, now it's -14. Again it is 6. Let me run it once more. 8. So do you see that the average is somewhere around 5 or something for being extremely careful? If we run it for being careful, the average will be slightly less than that, right? So I want you to like run it over 1,000 episodes for each action and then record those. So what is the average return if I always be careful like that? Okay, any doubts in this one? Is it clear what you need to do? It's already 1:37, so you don't have to do it now. Take a break and then do it, and you can submit it to me on Teams. And also, I'll check why this green line hasn't got printed on this one, and I'll fix it in the code. Okay. There are values, but it still did not print for some reason. I'll check that. Maybe there is a limit, some kind of limit. Don't know. I'll check that. Is it clear what you should run? Is there any doubt?
No, no.
Okay. And the quiz questions are here. The second part quiz. Try answering these and submit the answers to me once you're done. Okay. You can get them wrong. That is okay. Like, I encourage all of you to submit the answers. You'll get a good practice for the sessionals also. Sessionals are going to have similar questions. You can Google it. Don't ask ChatGPT, but you can Google and learn things and try to do it. Okay. And write it in your own words. In our company, when we ask ChatGPT for some documentations, we kind of mention in the prompt, like, explain in simple English so that people don't catch us, right?